Today we're going to talk about real-time clocks. They're normally an important part of a data acquisition and control system because they allow you to read the date and the time from a battery backed up clock and use that to timestamp any kind of data that's being logged to an SD card. Got three examples of a real-time clock here. Here's the DS1307, a very common board. Here's the actual real-time clock chip, crystal to provide oscillation, battery backup. In other words, this chip will continue to keep accurate time even if your Arduino is powered down. And some supporting circuitry. Notice that it has I2C interface, so it's fairly easy to connect to any kind of Arduino board. Here's another example. It's quite common and popular right now. The ZS-042, these are normally purchased on eBay. This is using a DS3201 chip. Also has an I2C interface. The battery is on the back, and in this case it's using a CR2032 battery. Now this board has to be modified a little bit to use safely with the Arduino, and we'll talk about that. Here's another example, the DS3234. Again, battery backup on the back side, and also is often used. Today we're going to use the DS3231. These can be purchased from $1 to $1.50 on eBay and have proven to be a really good workhorse for a lot of folks doing low-cost data acquisition. There's one very important thing to know, though, is that these were originally shipped with a rechargeable battery, but now because of regulations, most come without a battery. If you put a regular CR2032, this is a non-rechargeable battery, in this system, this has a battery charging circuit which will actually damage this battery and could even be a fire hazard. So you have to disable the charging circuit if you want to use a standard CR2032 battery. So what most of us do, let me show you one that hasn't been modified. Here's the original chip, and the charging circuit is right here where I have my pencil, and there's a resistor right here. What you can do is take your soldering iron and heat this up and just push it off of there, pop it off with a set of tweezers after the solder's been melted, and it will look like this now. That deactivates the charging circuit and allows you to use this with a regular CR2032 battery. This is a pretty important thing to do, otherwise you're going to have some problems and even some safety issues. So do not use this particular module unless you deactivate the charging circuit by removing that little resistor. Not hard to do, and you should have a soldering iron if you're working in this area anyway. Just heat that up and pop that off, and then we'll be ready to go. How do we attach that to our board? Here's my Arduino setup. I'm going to stick it on here. Now it's really designed for it has a vertical mount, which makes it a little bit hard to see, but you can still see the pin labeling here. I'm going to force it down into the breadboard, and now I'm going to make the connections. Notice I have my breadboard set up this time where I've run a pair of jumpers from 5-volt and ground over to the left hand side of the breadboard. That gives me a whole bunch of power and ground access points. So we're going to start out with ground. Power. Now we're ready to connect the I2C interface. Remember, there's clock and data. This time I'm going to use this other access port to I2C up here on the very outside of this header. Remember, we can access it in two locations here, pins A4 and A5, or at the very terminal end of this header. Clock goes to the very outside pin, and the data goes to the next pin. So it only requires 4 connections to connect the real-time clock to the Arduino board. Now let's load up a program and see if we can get this clock to work. Now, this system requires a library. There's lots of real-time clock libraries out there. This is the one we're going to use. It's on GitHub under Mr. Alvin, and it's been forked, meaning adapted from other real-time clock libraries. A lot coming from this G-Labs original library. So I'm going to download it to my download folder. I'm going to open my Arduino IDE, and I need to import that library. I'm going to go to Sketch, Include Library. This time I'm going to say Add Zip Library. I'm going to go to my Downloads folder. Here it is. It appears as rtclib-master. I'm going to click on that and open. And it says down here, library added to your libraries. Check Include Libraries menu. So I'm going to go back to Sketch, Include Library. And now you see there is a library here called Real-Time Clock Library. So that's a good sign. Now we have that available. Now, like a lot of libraries, this person has provided examples for reading the clock. But I'm going to load up one that I think is a little bit easier for you to use. And this is available through my website or through the Canvas system that we use here at CSU. But let me show it to you. It's just called Read and Set the Real-Time Clock. So let's look at it really quickly. So it has two include files, wire, which is our I2C interface, and the real-time clock library that we just imported. We set up the real-time clock objects. Note we have to tell it what kind of chip that we're using, in this case a DS3231. In the setup section that we only do once, we set up the serial interface so we can look at the serial monitor. We start the I2C interface, we start the clock, and then this is a very important statement right here. If we want to set the clock based on our computer's clock, we need to include this statement, rtc.adjust, and you see the grammar here. That will set the clock so it matches that of our computer. We only want to do that once, and then after that's done, we want to come down into this loop. This statement reads the clock, puts it into the object now, and then we can call that different variables from that object, the year, the month, the day, the hour, the minute, and the second. It's interesting, the DS3231 also has the ability to measure temperature, not very accurately, but it's kind of handy to be able to read temperature on the data logger itself. We call that panel temperature often. And so that should read the temperature on the chip and also print that to the screen. So since I don't know the history of this real-time clock module, the first time I use it, I definitely want to adjust, set the clock and get it set. So first I'm going to see if this compiles. It did compile. Now I'm going to hook up my Arduino. I'm going to make sure I have the right board and right COM port, and then I'm going to upload. Uploading is complete. Tools, serial monitor. Okay, and there it seems to be working. I'm getting the correct year, date, and time, and it is matching my computer. So at this point, the clock is set. What I'm going to do now is actually pull this out of the system. So it is disconnected from main power now, but it does have the battery, so it should keep time. So I should be able to lay that on my workbench even for days, and when I reconnect it to an Arduino and take a reading, it should take the correct answer. At this point, I'm actually going to upload modify the program. I'm going to delete out this section, or not delete, but comment it out. So now I'm going to upload this version. So this one, the version that's on the microprocessor now, does not reset the clock, does not read the computer's clock. It's just going to read whatever time is being kept in here right now, right? So I'm actually going to hook this back up, hit reset button. Now it should relaunch the program, and we'll see if it's still giving us the right answer. And it is. And you could obviously test this over longer periods of time just to verify for yourself. It's going to open another program now. This one's going to change the format a little bit. So I'm going to upload it. I've got this commented out. I don't want to reset the clock at this point. Let me show you what feature this one has that's kind of important. So this one, I want to output the time format like this: month, day, year, hour, minute, second. This is a nice format to go right into Microsoft Excel. One of the problems with how we were working before is that the system wouldn't put leading zeros on variables of only one digit. Let's say it's 2 o'clock in the morning. This would just appear as hour would appear as just the numeral 2, not 02. So I added a little subroutine down here called print digits, and it checks the number up here and sees if it's less than 10, and if so, it adds a 0 in front of it. And you can study that on your own to see how that works. But notice there's places up here when I'm wanting to print out the time, where I call that little function to make sure I have leading zeros on all my time variables that need it. Normally that's month, day, and then hour, minute, and second. So I'm going to upload this one now. Go to the serial monitor. And you can see here's an example. This very first row, it added a 0 in front of that 9. If I would not have had that subroutine, it just would have said :9. Now it says 09. That's a very desirable feature because we don't want the length of these strings to change, or we always want the leading zeros to be there. And we can watch it roll around to the top of the minute, and you can see it acting on the second. Now it happens to be, in this case, it's 12:48. But notice it also added a 0 for the month as well in front. So these leading zeros are being driven by that little function that I added. So here's an example where two are occurring, here and here. So that's a really handy thing to do often when you're building data acquisition systems. In the next step, I'll show you how to incorporate an SD card system into this, where we can take readings and then stamp this time as well as our data onto an SD card.